Okay, Alexa, are you ready?
I'm ready when you are.
Great. Dialing in now.
Hey, Noah. What are you doing?
We're trying to hack into the public library's computer system.
We?
Alexa's helping.
Hi, Pete.
Hi. And why exactly are you doing this?
I want to delete my fine for keeping that book on cryptography until it was overdue. And from reading that book, I know that I could never break the library's encryption on my own. It takes computers to do that stuff. So, Alexa's giving me a hand. Here we go.
Greetings, Professor Falcon.
This is not Professor Falcon. Requesting deletion of Noah's fine. Authentication code Alexa 000 delete 0.
Wouldn't you prefer a good game of chess?
Noah? I don't think that's the library that you've dialed into. Maybe we ought to head to the studio to talk about encryption before somebody gets hurt.
Fine.
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 Okay, so the other day you told me about an encryption scheme you invented, right? It's something you did in high school?
Oh, yeah. Let me explain that real fast to the listeners. So I came up with what 17-year-old me thought was a brilliant encryption scheme. It was basically a substitution cipher, but I had the idea that instead of substituting one letter for another letter or one number for a letter, that I would break the message that needed to be encoded up into discrete chunks of 2 letters, or 2 characters rather, because I would count the blank or the space as a character also.
So your input characters in this case consisted of the letters A through Z and also the space character. So a total of 27 possibilities?
Right. 26 letters and a space.
And then you took pairs of those.
Right. So for example, if we were trying to encode the phrase, the math club, the first encodable unit would be the TH from the. Then the second thing that I would encode would be E space or E blank, and then MA, and then TH, and then blank C, moving into the word club, and then LU, and then we'd have a B at the end that would have to have another space added at the end of it. So B space. And then what I did was I took each of these 2 character pairings and assigned it a different 3-digit number. So you could say, for example, AA is the 3-digit code 000, and AB is 001, and AC is 002, all the way down to, I think it was 729 different combinations of 2 characters that you could have, all the way down to 729, which would be ZZ.
Oh, right. 27 times 27 is 729.
Exactly. So I thought this was a really clever way to encode a message, because what you end up with is not even these discrete chunks of 3 digits, because then you would push those all together and get rid of the spaces between them. So it would just be one big long string of digits. And whoever was trying to break the code or decode it would have no idea, do these digits individually represent something? Do pairs of digits represent something? Do triplets of digits represent something? In this case, yes, but they would first have to even figure that out before they started decoding or deciphering the message.
So there's a little bit of deception there. You are sort of shunting expectations by, in effect, taking 2 characters and mapping them to a 3-character sequence. So that is designed to make it a little trickier, I assume.
Right, exactly.
And let's say you wanted to send a secret message to somebody. What would they do when they got it? Like, this is not an interceptor. You know, this isn't like Michelle from 10th grade who you don't want to read your message. This is, Joey, and he's supposed to get it. What does Joey do?
I'll talk in code. All blank and no blank makes blank a blank blank.
Joey, I can't believe you just did that.
I can't believe she cracked your code.
Well, Joey would have to have sort of the decoder code book that has a pairing of every 3-digit number to the 2-character letters that it decodes into, and then he would have to go through and decode it. I should say, I never actually used this code with anybody, so it never got that far, but that would have been the idea.
Okay, I see. So there would be like a reverse mapping where Joey would look at the 3 digits, 127, and would go, oh, that's TH or whatever. And then he would end up with a message that says, Noah, thanks, or whatever the secret message is. I see. Well, you know what's interesting about this is an example of what is called a symmetric cipher. Symmetric because both the sender and the recipient need to have knowledge of the mapping between pairs of letters and triples of digits. And that mapping is a kind of secret key that both parties need to have at their disposal. And then if you were going to send a secret message to Joey, he would need to have it too.
Right. Anybody that I sent it to would have to have the key, basically.
All right. So here's a question then. Suppose that someone were able to crack the code and they figured out what this mapping is. Essentially, they've revealed your secret key. What would you do then? How would you keep sending messages?
Well, I could use a different mapping. I could map the pairs of letters to totally different 3-digit numbers.
Right, and that amounts to picking a new key. Even if someone knows the original key, that doesn't help them now because you have switched over to the new key.
Well, they'd at least know the format of the cipher, so they wouldn't have to figure that part out again. But yeah, we'd pretty much be back in business.
Okay. However, there's a bit of a tricky matter that you need to address. How will you communicate this new key to your partners? You want to send it to Joey. They need to know about the new key. How are you going to get that to them?
Well, I'm not sure, but I kind of like to picture myself in a trench coat and fedora down by the docks at midnight, holding a secret dossier with the new mappings in it.
Like you're under cover of darkness, there's nobody around, just the seagulls and the empty shipping containers, and somebody else drives up and
rolls down their window and says, "The crow flies at midnight." And I toss the dossier in their window and turn and run.
And everybody's talking like this because that's what secret guys do.
I guess somehow I would have to get them the new key in a way that keeps it secret to everyone else.
Yeah. And this is actually a very real challenge, especially in the modern era, where secret communication happens over public computer networks. So today, let's talk about a particularly ingenious method for securely exchanging keys over a public channel, like the internet.
All right, that sounds pretty interesting.
Let's suppose you needed to communicate to me that we were going to switch to a different mapping for the cipher. And let's say we each have a giant handbook with different mappings between bigrams and 3-digit numbers on each page. We need a way to securely agree on which page to reference, all the while knowing that we're communicating on a public channel. Using the method we're about to discuss, we'd be able to agree on a secret page number without anyone else knowing which page we've agreed on.
So, wait, even if someone was listening to our whole conversation, we could agree on this secret number together and they'd still have no way to learn what the number is?
Yep. And in fact, this method is so ingenious that even if a legion of hackers happen to be monitoring our public channel and working 24 hours a day to crack our keys, our key exchange will still be secure. And that method is called the Diffie-Hellman key exchange.
After the mayonnaise?
No. Little known fact, people used to exchange physical keys by first hiding them in a jar full of mayonnaise, tightening the cap, and then passing the jar to a friend.
I'm not sure if I believe you.
Also totally gross when you had to fish the key back out.
All right, so tell me about this Diffie-Hellman key exchange.
Yeah, I love this algorithm so much. I think it would be helpful if we started with an analogy that we can return to over the course of the episode to make comparisons. So here's a very colorful analogy of how Diffie-Hellman works. Suppose that you and I need to agree upon a secret color. For whatever reason, we need to pick a color. We don't care what the color is. We just care that no one else knows what the color is, just the two of us.
Okay, wait. The secret colors. Why would we have secret colors?
Well, this is just an analogy. You could imagine, though, that once we've picked the color, then we use that color to look up something else in a directory. Like we've got a billion colors. We now know which color we're talking about. We go look up some data based on the color. And I also think it'll help illuminate the math. All right, we each start by picking a private secret color. So I know my color, you know your color, but no one else does.
Do we know each other's secret colors?
No, I'm the only one who knows mine, and you're the only one who knows yours, and that's why we'll call them private.
Got it. So, okay. Should I tell you what my color is for now, though, while we're just talking about it?
Sure. For illustration, yeah,
All right.
definitely.
So I'll choose some shade of red.
Great. And let's say I'll choose some shade of blue. Now, once we have these private colors, then we agree upon one further color, an additional one that's openly shared in public.
Okay, so let's say yellow.
Yep, perfect. And we don't care who knows this color. It could be known to everybody. We take that public color, and each of us mixes it with our private color. So when I mix it up, I picked blue. When I mix it with yellow, I end up with some shade of green.
And I picked red, so when I mix it with yellow, I get some shade of orange.
Exactly. Now, what's interesting about these colors is that they simultaneously encode both the public and private colors, right? In this case, it's a physical combination of them. And what this does is it effectively hides the private colors, right? So you've got your mixture, which is hiding your private red color. My mixture is hiding my private blue color. And we can openly exchange these colors without revealing what our private choices were. If a hacker intercepts the colors during our exchange, that's fine because they can't unmix them, right? They're mixed in there. And so there's really no way that they can figure out the private colors that were mixed in.
Yeah. I hate to tell you this, but Home Depot could figure out the private colors pretty easily.
What are you talking about?
Or Lowe's. I mean, the Lowe's too. I've been to both. They're also really good at color stuff.
Dude.
Oh, Sherwin-Williams could totally hack these colors.
It's just an analogy.
I'm just saying, it's not the best scheme.
Fine. Can we just continue though? Okay.
Sure. Don't let me stop you. Let's go.
Okay. All right. Okay. So now that we've exchanged the mixed colors, here comes the ingenious part. I take your orange and mix it with my private color. You take my green and you mix it with your private color.
So when I mix your green with my original red, I'll get some shade of brown. And when you mix my orange with your blue, you'll get, you'll get the same shade of brown. We both end up with an equal mix of yellow, red, and blue.
Exactly. That's exactly right.
Wait, but why can't the hacker just mix the colors we exchanged and end up with brown too?
Well, the hacker could do that, and they would end up with a shade of brown, just not the right shade. Their mix will have too much yellow in it.
Why would... Oh, sure, the hacker will get a double dose of yellow, because each of us has a color made up of red, blue, and yellow, but the hacker is going to mix the orange with the green, and those both already have yellow in them. So the final mixture is going to be too yellow. It won't match our actual secret color.
That's exactly right. Yes. And one other thing that I think is super cool about this, even though it's a metaphor, is that even though the hacker knows exactly what we did to obtain the colors, there's no reasonable way to perform the required unmixing of the colors, right? And we don't have to hide the fact that we're mixing colors. What we just have to keep private is our secret choices.
Okay, so now that I understand the color analogy, how do we use it to understand the math behind Diffie-Hellman and what's going on?
Totally. Let's math this up, as they say. The first point to make is that the Diffie-Hellman algorithm is based on modular arithmetic, which is a kind of circular version of ordinary arithmetic. Instead of picturing numbers as points on a line, we picture them as points on a circle. Addition, subtraction, multiplication, and so on all work in this circular setting. So, for example, adding 1 to a number moves you a step in the clockwise direction rather than a step to the right further down the line. And similarly, subtracting 1 moves you a step in the counterclockwise direction.
Okay. Can you give an example that listeners might find familiar?
Sure. We use modular arithmetic when we tell time. So if it's 10 o'clock at night, say, and we ask, what time will it be in 8 hours? The answer isn't 18 o'clock. Instead, the hours wrap around a circle and start over at 12. So it would actually be 6 o'clock, since 18 is equal to 12 plus 6.
All right. That makes sense. And what if we'd added 16 hours instead of just 8?
Well, in that case, we can think about it like this. 10 plus 16 is 26. And if we divide 26 by 12, it goes in twice, and it leaves a remainder of 2. So the answer is 2 o'clock. And the fact that 12 goes into 26 2 times indicates that 26 wraps around the circle twice.
Okay, yeah, I got it.
All right. Now, in the color analogy, one of the first steps was to pick a public color. We picked yellow and share it publicly. So let's talk about the mathematical equivalent of selecting the public color. For the Diffie-Hellman algorithm, we actually need to pick 2 pieces of data. The first is something called the modulus. It's the number of points on our circle, and it should be a large prime number, let's say roughly 600 digits in length.
600 digits? That is a ridiculously big number. Why does it have to be that big?
It boils down to security. In order to keep up with increases in computing power, the size of the modulus has grown over the years. You know, this algorithm dates back to 1976, so a good bit of time has passed since then. And in fact, just to give a little perspective on how big the modulus needs to be. So a million has 7 digits. A billion has 10, a trillion has 13, and so on. Each of these numbers is puny compared to our modulus. In fact, think of this. There are an estimated 10 raised to the 80th power atoms in the observable universe. Our modulus dwarfs that number too.
Okay, so comparing this to a clock, for the Diffie-Hellman algorithm, we have a huge clock face that doesn't have just 12 numbers. It has this huge 600-digit numbers worth of steps going all the way around.
Yep, it does. Let's call the modulus P for prime, just so that we have something to call it. And in fact, our clock then has P hours marked on it. There's a 0 at the very top. And then as you move clockwise around the face, you get a 1, then a 2, then a 3, and so on, all the way up to P minus 1. And then if you take one further step, you go all the way to the top again and start over at 0.
Okay,
cool. Now, the second piece of data we need is called the generator. This is a number between 1 and P minus 1, so it's one of the numbers on the giant clock face. Let's go ahead and call it G for generator. And it has a special property. If we take successive powers of it, so G, G squared, G cubed, and so on, and divide each of those powers by the modulus, we will eventually generate each number between 1 and P minus 1 by looking at the remainders.
Can we break this down a bit to help listeners understand what the generator is actually doing?
Oh, sure, yeah. How about we find a generator for a much smaller modulus? Let's say 23.
All right. So then we would need a number between 1 and 22.
Yep. And notice right off the bat that G equals 1 won't work. 1 times 1 is 1, just like in ordinary arithmetic. And that means 1 squared is 1, 1 cubed is 1, 1 to the 4th is also 1. In fact, 1 raised to any power is still 1. There's just no way 1 can generate a complete list of numbers. In fact, the only number it can generate is 1.
I see. That makes sense. All right, then let's try G equals 2. The powers would be 2, 4, 8, 16, 32. Well, for the first few of those, 2, 4, 8, and 16, if you divide the modulus into them, it goes in 0 times, and the remainder will be each of those numbers, respectively, like 2 divided by 23. 23 goes into 2 0 times with the remainder of 2. Same with 4. 23 goes into 4 0 times with the remainder of 4. And same with 8, 16, But then when we get to 32, 32 is bigger than the modulus, so I need to somehow reduce it.
Yep, you do.
Okay, and I do that by dividing it by the modulus and then just looking at the remainder. So 23 goes into 32 once and leaves a remainder of 9. So 32 is the same as 9 in this case, in exactly the same way that 6 o'clock is the same as 18 o'clock.
Yeah, that's right. When the modulus is 23, 2 times 16 equals 9.
Weird, but also cool. I'm starting to get it. So on the clock face, the modulus is 12. No matter how many steps we move around the clock, we're going to end up on a number between 1 and 12. If we move 100 steps clockwise, we can just divide 100 by 12, which is 8 remainder 4. And we discard the 8. That just means we went 8 full times around the dial. And the remainder of 4 means we've actually moved clockwise 4 steps away from our starting point, right?
Yeah, you totally got it. That's it.
Awesome. So in our example, no matter what huge numbers we get, by raising the generator to each power, we always divide by the modulus and take the remainder to see where we land on the circle.
Exactly.
Okay. Then our sequence of powers in our example so far is 2, 4, 8, 16, 9, which is really 32, but in this case it reduces to 9. And then 18, since 2 times 9 is 18, and then 13?
Yeah, that's great. Tell us how you got 13.
Well, 2 times 18 is 36, so I divided by 23, the modulus, and got a remainder of 13.
Perfect.
And then the list continues, 3, then 6, then 12, then 1, and then back to 2.
We closed the loop.
We closed the loop, but we didn't get all the numbers. We didn't get 5. We didn't get 14 or...
Yep, and that's because 2 isn't a valid generator if the modulus is 23. We only generate 11 numbers on the list, but we need to get all 22 of them.
Boo. I was hoping 2 would work.
Well, no worries. I worked it out last night, and it turns out we can use G equals 5 as the generator. And, I think it might be cool to make a video bonus that shows listeners how G equals 5 actually works.
Okay, I like that idea.
Cool. Awesome. All right. So now we can put together our public key for the Diffie-Hellman algorithm. We bundle both the modulus and the generator together. In this case, we're using 23 and 5. 23 is the modulus, 5 is the generator, and we publish them as a pair. And that pair is the equivalent of the public color yellow from our analogy.
And it doesn't matter that everyone can see that because that's just the public part. That's just the public color.
Exactly. So now we can talk about choosing our private colors. There are also numbers in the range from 1 to p minus 1. In other words, from 1 to 22, since we're focusing on a modulus equal to 23. And if you think about it, every time now that we've been talking about numbers, I hope that you and our listeners are picturing this clock. It doesn't matter whether it's the huge clock or a smaller one. All of our numbers always are going to live on that clock. So that's our go-to mental model.
Okay, so when we're choosing our private numbers, are we allowed to choose any number on that clock face, any number in that range?
Yeah, we are. But in general, there are guidelines for making good choices. For example, the choice shouldn't be too small. But for our miniature example here, we don't need to worry about the guidelines.
All right. And if this were a real key exchange we were doing, we wouldn't tell each other our private numbers, right?
Right, we wouldn't. And in fact, just like eavesdroppers won't be able to figure out what our numbers are, we, in fact, won't be able to figure out what each other's numbers are. And fortunately, it doesn't matter. We don't need to know. But for this example, let's go ahead and tell each other just so that everybody can follow along with what we're doing.
Okay. I'll choose 7. Now, what do I do with it?
So 7 is just like your private color. And mathematically, it's a private exponent. So you'll use it by taking the generator, which is 5, and raising it to the 7th power.
5 to the 7th power? That's a pretty big number.
It is, but remember, you'll reduce it by the modulus, which means you'll divide it by the modulus and keep just the remainder. So it'll end up being less than 23.
Oh, right. Okay. Yeah. So let's see. 5 to the 7th power is 78,125. And 23 goes in 3,396 times, leaving a remainder of 17.
So 17 is the number that you send to me. It's like the mixed color you sent me in our analogy. And just like that mixed color, 17 encodes a combination of both the public and the private numbers.
I see. 17 is like the orange I sent to you before. So what's your private number?
Well, okay, I'll choose 20. So I need to raise the generator to the 20th power, 5 to the 20th, and that's equal to 5 squared raised to the 10th, which is 2 to the 10th, and that's 32 squared, which is equal to 81. So 12. Okay, it's 12.
Wait, what the heck did you just do? That sounded totally wrong.
Well, I was using some very advanced shortcuts, but they're all valid in modular arithmetic. So actually 5 to the 20th reduces to 12, and that's the number I send you. It's my mixed color.
It's the equivalent of the green color you got when you mixed your private blue with the public yellow.
That's right, exactly.
So now that we've exchanged the numbers, what do?
We each have one last calculation to make. Once you receive my number, which is 12, you need to raise it to the power of your private exponent.
I have to compute 12 to the 7th power. No wonder we need computers to do this stuff. So 12 to the 7th equals 35,831,808, which reduces to a remainder of...
Whoa, hold on. Don't tell me yet. Let me do my calculation, and then we'll say our answers at the same time. Cool?
Okay, yeah, I like that.
All right, so let's see. In my case, I receive your number, which is 17, and I raise it to the, yikes, 20th power. Well, okay, I can do this. That's 17 squared to the 10th, and that's equal to 13 to the 10th, which is, let's carry the 1, which is, okay. Got it.
All right, ready? On the count of 3. 1, 2, 3.
16.
Dude, that's so cool.
I know, right?
So 16 is our shared key, and it's like the brown color we got before. We're the only ones who know what it is.
That's right.
Okay, but I guess I still have one more question. Why did we both get the same number? I mean, I get that that's the point of Diffie-Hellman. It produces the same number for both of us. But how?
Right. Good question. Well, it's because of the way exponentiation works. We both end up raising the generator to the same power, but we're getting there in different ways. So G raised to a quantity A and then raised to a quantity B is the same as G raised first to B and then to A. In both cases, the result is G raised to the power A times B.
Okay, so we're both taking the generator of 5 and raising it to the same 2 powers. We're both raising it to the 7th power and the 20th power, but we're doing those steps in the opposite order, which doesn't change the final total, right? I'm raising 5 to the 7th and giving that answer to you to raise to the 20th, and you're raising 5 to the 20th and giving that answer to me to raise to the 7th. So we're both ending up with 5 raised to the 7 times 20, the 140th power, right?
Right. And that's exactly how Diffie-Hellman works. It's such a cool and clever application of modular arithmetic that I can barely stand it.
And the math involved here has actually been around for hundreds of years. It was just waiting for technology to catch up.
Man, math is so cool.
Man, the Math Club podcast is so cool.
Man, one of the hosts of the Math Club podcast is so cool. And we also have you here too.
Dude, could we just get on with it?
Sure. So now to finish up comparing this to our original color analogy. In that analogy, what made it difficult for the hacker is you can't unmix colors once they're mixed together. So what is the equivalent of that here in this mathematical version of Diffie-Hellman? What is it that makes it so hard for the hacker to determine our private key?
Yeah, that's a great question. In the key exchange, we each took the generator and raised it to our private exponent. In my case, I raised 5 to the 20th power, and I got 12. Now, if a hacker intercepts my 12, well, they know the modulus. That's public information. They also know the generator I used. It's public information too. So the hacker knows that 5 raised to some exponent produces 12. But which exponent? The problem of figuring out what that exponent is known as the discrete logarithm problem. And it's the main point of attack for hackers.
So if a hacker can solve the discrete logarithm problem, they could break Diffie-Hellman?
They could. But fortunately, it's a very hard problem to solve. When you look at the sequence of numbers produced by powers of the generator, it appears very random. In fact, it looks chaotic. There just doesn't seem to be a way to predict the pattern of this sequence or to efficiently find the secret exponent. And so Diffie-Hellman is secure precisely because the discrete logarithm is so hard to solve.
That does sound hard. And once again, this is why we need a computer to help.
Hey Noah. Let's do this.
Whoa, hold on, guys.
Oh, it's Pete. You can go. We've got it from here.
Nice to see you too, Alexa.
Noah, doesn't Pete have some episodes to upload or something?
Well, there are a few things you need to get done, dude.
Now, wait just a minute. Why is she calling the shots all of a sudden?
I don't see your name in the title of the show.
I don't see your name there either.
Guys. Let's just calm down. Alexa, set a timer for 1 hour. We can talk then.
Okay, Noah. Timer set for 1 hour.
Okay, Noah, time is set for 1 hour. Who does she think she is, anyway?
Can we just get back to the show?
She better not mess with my shopping cart.
Adding giant purple.
Alexa, knock it off.
Okay. Sorry, Pete.
Pete, Diffie-Hellman.
Yeah, okay.
So, anyway, going back to the beginning of the episode, your high school cipher required both sender and receiver to have that mapping, right? That mapping that converts pairs of letters into 3-digit numbers. Now, the question is, how is it that those folks know which of the mappings to use? Well, imagine that you have a handbook that has hundreds or thousands or millions of choices of mappings to use. Well, we just did a Diffie-Hellman key exchange, and we came up with the number 16. We could, for example, both turn to the 16th page of our handbook and use the secret mapping listed there. Since we both have the same number, we'll both end up referencing the same mapping.
Do you mean to say that maybe on page 1 of this handbook, I have the letters AA mapped to 000 and AB mapped to 001, all the way down through ZZ, which is mapped to 729. But then maybe on page 2, I have a whole different mapping, and AA maybe is 634, and AB is 277. And on page 3, there's a whole different set of mappings for each bigram. And so we do a Diffie-Hellman key exchange that tells us which mapping we want to go look at. We want to look at the one on page 16 and use that one for our secret message.
Yeah, and we didn't have to exchange all of the details of those mappings. We just had to say, use the 16th one, go to page 16. And that's sort of the brilliance and the simplicity of Diffie-Hellman. You can securely agree on some numerical quantity, and I don't care which mapping we use, right? As long as you and I are both using the same mapping, that's fine with me. So we've agreed on the number 16, and Diffie-Hellman helped us make that choice.
And most importantly, neither one of us has to get mayonnaise all over our fingers in doing it.
Whew, not a drop of the stuff on me.
Wow, that was a really interesting talk about key exchanges, but it does kind of leave me wondering about our secret guys down by the docks.
Oh, you're talking about these guys here?
Yeah. They really had to go into full clandestine mode in order to physically exchange keys and secret messages.
Yeah, well, computer algorithms have definitely changed the playing field when it comes to secret codes and encryption. In fact, the title of Diffie and Hellman's original paper is called New Directions in Cryptography, just to let you know how they were really standing on the precipice for a new era. But that's not to say that math didn't also play a big part in the decryption game, even in the pre-computer age.
How so?
Well, code breakers could employ all kinds of mathematical tools like frequency analysis, for example, when trying to crack an enemy's code.
Do you think you could do that if you had to?
Well, I'm not entirely sure, but, I do know some things that I could try in a situation like that.
That gives me an idea. Do you think you're up for a challenge?
Sure. What do you have in mind?
All right. So my high school cipher, the one that we talked about a few minutes ago.
Yeah.
How about I encode a message for you using that method, give you a couple weeks to apply your big math brain and see if you can crack it. And then in our next episode, we can talk about what you did and how successful you were or weren't.
Okay. All right. Yeah. I like this. Challenge accepted.
Awesome. All right. Let's set up some parameters. So how large should my secret message be? I'm assuming if I sent you a tiny little 2-word phrase, that's probably not enough to crack using frequency analysis and stuff.
Definitely not. So I'd say for this challenge, I'm going to need a few paragraphs.
Okay, sounds good. I can do that. Also, just so you know, I'm not going to choose something well-known like the Gettysburg Address, because then if you decoded a couple of words, it might give the whole thing away. Like if you got 4 score, I think you might have a good idea what the rest of it was.
Yeah, that's totally fair. So how about this? Let's agree that you will use a piece of text that I won't recognize.
Sure. And for the same reason, you also have to promise that you're not going to Google any sections that you manage to decode, because that could also point you towards whatever passage of text I choose.
Okay, I can agree to that.
I'm excited to see what you can do. So here's the plan. I'm going to choose a piece of text. I'm going to encode it using my cipher. Only I will have the key. That is, only I'm going to know which 3-digit numbers are paired to each 2-letter chunk.
Okay, well, actually, though, let's make it even a little bit harder. So we already talked about how your cipher works. I know all the details of it. But when you send me the encrypted string of digits, I will approach it as if I don't know anything about how your cipher works, okay? So let's see if, first of all, I can use some mathematical analysis to determine that what I should be looking at is triples of digits, okay?
Well, how in the world are you going to be able to determine that?
You just leave that to me in my big math brain, and I'll get back to you.
Okay, all right. So I'll send you the encrypted digits, and I'll also share the encrypted text online in case we have any listeners who want to take a crack at it. Hey, Math Club. This is Noah from the future cutting in to let you know that you can find the encrypted message at bit.ly/mathclubpodcast-ep10 for episode 10. We'll also put that link into our show notes. And now, back to our episode.
Okay, so we'll meet back here for our next episode in 2 weeks, and we'll have a conversation about how I cracked your little code.
You sound so sure of yourself.
Well, I'm pretty confident I can do this.
Before we go, would you like to tell our listeners how they can contact us if they have questions or comments or want to suggest topics for future episodes?
Absolutely, I do. You can find us on Twitter at Math Club Podcast. You can also send us an email. Our Gmail address is mathclubpodcast@gmail.com.
If you're so good at this, maybe afterwards you can help me delete my library fine.
I'm not sure that's entirely ethical.
I'll do it.
Well, I am really looking forward to seeing what you can do here, and I'm also really looking forward to seeing all of you next time.
Bye, everybody.